Alright, welcome to practice exam 4 for Math 147 Calc 1. Let's go ahead and get started. Our first problem here, we're asked to find the answer for a Riemann sum. Remember, that's just a fancy term for saying add up approximating rectangles. And our function is x squared minus 2x, interval is 2 to 10, and we're using the midpoint and 4 subintervals. So what I like to do is draw a picture of what the interval looks like here, and then mark off where my subintervals are going to be. So here's 2, and let's see here, 4, 6, 8, 10. So since there's 4 subintervals, each base is going to be 2 units wide. And then we are using the midpoints to get the height. So we'll mark off our midpoints, which are at 3, 5, 7, and 9. So those are the points that we're going to plug in to get the height. Our base is going to be 2 units. So our delta x here is going to be 10 minus 2, b minus a over n, and n equals 4. So that's 8 over 4, which is 2. So all our bases are 2. So our area is going to be approximately equal to the sum of base times height. Alright, all your bases are 2. Your first height is going to be function value at 3. So it's going to be f at 3 is our height times our base, which is 2. And then in our second rectangle, we're using 5 to get the height. So f plug in 5 times 2. Third rectangle, we're plugging in 7. Fourth rectangle, we're plugging in 9. So f of 7 times 2 plus f of 9 times 2. So now just plug your values into your function x squared minus 2x. So 3 squared minus 2 times 3, that'd be 9 minus 6, which is 3, times our 2. Plus, now plug 5 in. 5 squared is 25 minus 2 times 5. 25 minus 10, 15 times 2. And then let's see here, plug 7 in. So 7 squared is 49 minus 14 is 35. So 35 times 2. And then plug 9 in. 9 squared is 81. Minus 18, so 71, 61, 63 times 2. And of course you can do this in the calculator. I'm doing the math in my head. And then just multiply these and add them all up on the calculator and you get 232, which is C. And some of my distractor answers are going to be if you use the left endpoints, 2, 4, 6, 8, or if you use the right endpoints, 4, 6, 8, 10, things like that. Number 2, we need to decide which integral is represented by this sum. And the key is out here, you look at this 5 over n, and you also see a 5 over n in there. That's going to be your delta x. Okay, so this guy out here, that's your delta x, which is b minus a over n. So b minus a is 5. So the distance between a and b, the lower and upper limits, is 5. So you look at all of these. So this is from 1 to 5. That's only 4 units apart. So that one's out right away. 1 to 6. 6 minus 1 is 5. That's a possibility. 6 minus 1 is 5. 5 minus 0 is 5. So we already ruled out one of them. And then this guy in here, 1 plus, this is 1 plus I times 5 over n. That is our x sub I. That's our general right endpoint. And remember that the general formula for this is a plus I times delta x. So that means our a has to be 1. So this integral has to start at 1, and then it's 5 units between A and B, so it has to go from 1 to 6. Okay, that 1, that's our starting point. So that rules out this one because it goes 0 to 5. So now it's one of these two guys. All right, so what happens to our x of I that we put in, this quantity 1 plus 5i over n, or 1 plus I times 5 over n, our right endpoint? Well, in the limit, this x of I gets replaced by an x, so this whole thing becomes our x. So in the limit, this is our x, so this is going to be 2 minus x squared. So this is going to correspond to 2 minus, and just the x gets squared, right? Here's our x of I, it gets squared. So 2 minus x squared is this part in here. And then this is the delta x, which turns into dx. And then in the limit, this sum turns into an integral. And we already said that the starting point was at 1. And then b minus a is 5, so it's got to go up to 6. So 2 minus x squared, that's this guy right here, b. So now, and then notice here another good distractor would have been 2 minus x quantity squared. Okay. So that would be if the square went on the whole thing. And then this one here, the 2 minus 1 plus x squared, that was if you chose your xi just to be 5i over n. But if that was the case, you wouldn't be starting at 1, you'd be starting at 0. So the easiest way is just take whatever's inside those inner parentheses, let that be your x of I, match up your a, which is 1, and match up your delta x, which is, in this case, 5 over n. Okay, number 3, we're going the other way. We're given the function, we're given the starting and ending points, so this is your a, this is your b, and they want us to match up the right limit. Well, first of all, let's see what delta x is. So your delta x here is b minus a over n, so 4 minus 2 over n, which is 2 over n. And remember, all of these things are adding up base times height. So this is your height, this is your base, 2 over n. This part is your height, base, 2 over n. This is your height, base, 1 over n. Oh, that guy's out. And then this is your height, and base 4 over n. That guy's out. So now it's either a, b, or none of these. Alright, well, what next? Well, our function is sine x times cosine x. So let's see here, I see sine plug in cosine of x. That's no good. Sine of a value times cosine of a value, that's a possibility. So this one's out because this is a composition. See, this is sine plug in cosine 2 plus 2i over n. So that guy's out. So this is our main candidate. If that doesn't match up, then it's none of these. Okay, what next? Well, what you're plugging in for your x there, when you do the limit, is xi. And remember that x of I is a plus I times delta x. And here we know what our a is. It's 2 plus I, and then our delta x right here, 2 over n, which is the same thing as 2 plus 2i over n. So this quantity, 2 plus 2i over n, that's going to get plugged in here for x, and then also here for x. And in fact, that's exactly what they did here. There's your xi, there's your xi, 2i over n. So this quantity here is f plug in x of I, or f plug in the 2 plus 2i over n. So that does indeed match up. So this is B. Number 4, we're using the additive property of integrals. So the integral from 0 to 6 is 8, 0 to 2 is negative 3, and 5 to 6 is 4, and we want to find 2 to 5. Okay, well, let's see, the biggest one is from x equals 0 to x equals 6. So the integral from 0 to 6 of f of x has got to equal the integral from 0 to 2 plus the integral from 2 to 5 plus the integral from 5 to 6. So areas are additive. So this has got to equal the integral from 0 to 2 of f of x plus the integral from 2 to 5 of f of x plus the integral from 5 to 6. Those are our three pieces of f of x. And notice how, see, this starts at 0, ends at 2, and this picks up where the previous left off, starts at 2, ends at 5. This one starts at 5, ends at 6. So this is saying the area underneath the graph from 0 to 6 is just the area under the graph from 0 to 2 plus the area from 2 to 5 plus the area from 5 to 6. Okay, so now plug in the things we know. So area from 0 to 6 is 8 on the left hand side, and that's got to equal 0 to 2 is negative 3 plus 2 to 5, that's our unknown, so let's call it A for area. And then on the last piece here, 5 to 6, that's 4. So now solve for our area. So negative 3 and positive 4 is a positive 1. So this is saying 8 equals A plus 1. And then bring that over as a negative. So A has to equal 7. Subtract 1 on both sides. So C. Okay, and your picture is you're thinking of areas adding up. So for example, here, sketch a picture down here. Here's our y equals f of x. And we're finding the area from x equals 0 all the way out to x equals 6. So that area, that total, is 8. And then they tell us from 0 to 2, it's negative 3. So that's saying that the area is 3, but it's below the axis. So I'm going to attach a negative in there. Let's see, from 2 to 5 is what we want. So this is the area we don't know. And then from 5 to 6 is 4. So this has to be a 4. But then the total of all these areas has to be 8. So that's kind of the picture that goes with it. Except that this part should actually be below the axis because that's negative. Integral is negative. Remember, it's signed area. All right, and number 5, they just want us to write the integral that gives the area under x cubed plus 1 over x from 4 to 9. Okay, well, definite integral is signed area. Okay, so our area is just going to be the integral from 4 to 9, starting at 4, ending at 9, of this function, x cubed plus 1 over x with respect to x. Now, if this was area in between two functions, then we'd have a little bit more work. But this is just area underneath one function, and the definite integral is signed area. Okay, number 6, we've got an absolute value function. We're integrating from 0 to 5, so we're finding the area underneath this function. And I mentioned it's easiest to do this geometrically. So if we sketch a graph of this function, let me do it up here if you don't mind. Absolute value of x is a v-shaped function at 0, like this. That's absolute value of x. And then if we're doing absolute value of x minus 2, so we added a negative, or we subtracted 2 on the inside. Remember, that gives us a right shift of 2 units. If you add on the inside, it's a left shift. If you subtract, it's a right shift. So this is the v-shaped curve, and it's shifted 2 units to the right. So it looks like that. And we're integrating from 0 to 5. So here's 0, 1, 2, 3, 4, and 5. So we want these two areas. Well, they're two triangles. And remember the absolute value function, this has a slope of 1 because the absolute value is x if x is positive, and it's negative x if x is negative. So this has got a slope of negative 1. So that means that this thing hits up here at 2, and then this height is going to be the same as the base, 3. So we've just got two triangles with base and height are the same. So the area of this triangle is going to be 1/2 base times height. Base is 2, height is 2. So 1/2 times 2 times 2 is going to give this area, which is just going to be 2. And then this one in here is going to be, again, 1/2 base times height. So 1/2 times base times height, 3 times 3. So that's 9/2. So 2 plus 9/2. So 9/2 is 4.5 plus another 2, 6.5. Right, there we go. So we're just adding up areas of geometric figures, just interpreting the definite integral as area, signed area, and both our areas are above the x-axis, so they're both positive. And then just using triangles, rectangles, etc. So that's what I mean by geometrically draw the graph. That's the easiest way to do that one. Number 7, here we're using fundamental theorem because we did an integral from 0 to x and then derivative with respect to x. So this x and this x are the same. So by fundamental theorem, these are inverses of each other. They undo each other. So you just get this function back again, but evaluate it at x instead of t. So this will be sine of x over x plus 1. And remember the theorem that I'm using is this one, that the derivative with respect to x of the integral from a number a up to x of f of t dt is equal to, you started with f, you did an integral, you did a derivative, they undo each other, you get back to the function f, but at x instead of 0. Or I'm sorry, instead of t. T is just our variable of integration. So that is this guy right here. And notice that these two are different. Okay, because here x is the variable that we're integrating with respect to. I'm sorry, x is the variable that's the upper limit of integration. T is the variable that we're integrating with respect to dt. So not a whole lot of work to show there. We're just using that formula. What is the proper u substitution to evaluate this integral? So you look for a function and its derivative, let u equal the function. So here I see a 2t to the 5th, and then derivative of that would be 5 times 2, 10t to the 4th. Here's our t to the 4th. So I think this inside right here, that'd be our best choice for u. 2t to the 5th, which is d. And then we are evaluating some integrals here. So remember, when you're dividing here, what you want to do is you want to write this as a negative exponent up on top and then multiply it through. So this is going to be integral, and then change this to a fraction exponent. So that t cubed is going to come up to the top as t to the negative 3. And we are going to be multiplying by this guy, which is t to the 1/5. Fifth root is 1/5 power, plus 3t minus 1. And now we multiply this in times each piece. Remember, we're trying to just get all powers so we can use power rule. So when you multiply, you add exponents. So a negative 3 and a positive 1/5. So this is negative 15/5 plus 1/5 is going to be negative 14/5. Just getting a common denominator. And then when we multiply these guys, negative 3 and then a positive 1 is going to give negative 2 exponent. So plus 3t to the negative 2. And then t to the negative 3 times negative 1 minus t to the negative 3. And we still need to do an integral with respect to t. Actually forgot my dt here. Okay, so now we take our antiderivative. So this is just power rule. So because everything's t to a power, so add 1 to the exponent and divide by the new exponent. So this is going to be t negative 14 fifths plus 5 fifths. So that would be negative 9 fifths. And then divide by negative 9 fifths, which is the same as multiply by negative 5 ninths. Plus 3. Add 1 to this exponent, we get t to the negative 1. So t to the negative 1 divide by negative 1. And minus. Add 1 to this exponent, we get t to the negative 2. So t to the negative 2 divide by negative 2. And then plus a constant because this is indefinite integral. And a little bit of simplifying here. Well, actually, you don't have to simplify on the exam, but notice here double negative would make a positive. This negative we could bring out in front. So this would be negative 5 ninths t to the negative 9 fifths. And then let's see here. T to the negative 2 on the top is t squared on the bottom. So this is plus 1 over 2t squared. And then, oh wait, that's this last term. I skipped a term. Move that guy over. Here, t to the negative 1 on the top is t to the positive 1 on the bottom. And this negative we can pull out in front. So it'd be negative 3 is still on the top, and we've got t on the bottom, t to the first, and then plus c on the end. Okay, now we've got a definite integral, y times y minus 1 squared. Now there's a couple things you could do on this one. You could use a u substitution, or you could multiply this whole thing out. So you could just multiply this all out, FOIL y minus 1 squared, and then multiply the y in. I think that's actually going to be the easier choice in this case. So y minus 1 times y minus 1, and then y out in front. So first terms give us y squared. Outer terms negative y, inner terms negative y, so it's negative 2y. Last terms plus 1. And then we've got y out in front. That needs to be multiplied in times each term. So this is going to be y cubed, y times y squared, y cubed, minus y times 2y, 2y squared, and then y times 1 plus y. So this is going to be integral 0 to 1, y cubed minus 2y squared plus y, all with respect to y. So now we're ready to integrate. So this is going to be power rule on each piece. So we increase the exponent, divide by the new exponent. So the first one is y to the 4th, divide by 4. And then minus 2, antiderivative of y squared is y cubed over 3. And then plus, this is y to the 1st, so antiderivative y squared over 2. And we are evaluating from 0 to 1. So plug in 1, plug in 0, subtract, and we're done. So if you plug a 1 in, here, 1 to any power is just 1, so that's going to be 1/4 minus 2/3 plus 1/2. And then if you plug in 0, you just get 0, 0, 0. So minus 0. And then this is just calculator work here. But if you get a common denominator and combine these, you get 1/12. Next up, we got another definite integral. Looks like we're going to need to use substitution here. I see a function and its derivative. Actually, these are basically derivatives of each other, but we don't want to let u equal cosine of theta, because then our du is going to be inside the square root. And in fact, what we'd like to have is we'd like this to be just square root of u, because that's u to the 1/2 power, and then we can bring that up to the top and integrate it. So I look at this and I say, well, let's let this inside function sine theta, let's let that be our u. And then the derivative of u, or the differential of u, then is going to be cosine theta d theta. So then here's our u, and then up here on top, here's our du. Right there. So the 3, we can factor that out. 3 comes out in front. And now we've got integral. Up on top, we've got du, or 1 du if you want. On the bottom, just square root of u. And then we have to change these theta values over to u. So if theta equals 0, then plug that into our equation for u, our substitution. Then u is going to equal the sine of 0, which is just 0. So this stays at 0. And then if theta equals pi over 4 up here, then our u is going to be sine of pi over 4, which is root 2 over 2. That's from the unit circle. So this one is root 2 over 2. So then this is again u to the 1/2 on the bottom. So this is going to be 3 times the integral from 0 to root 2 over 2 of du over u to the 1/2. And then positive exponent on the bottom is going to be negative on the top. So this is 3 times the integral from 0 to root 2 over 2 of u to the negative 1/2 du. And now we're ready to find our antiderivative, and this is just going to be power rule. So add 1 to the exponent. Negative 1/2 plus 1 is positive 1/2. So we got our 3 out in front. U to the positive 1/2, and then divide by the new exponent. So dividing by 1/2 is the same as multiplying by 2 over 1. So I'm going to do that. And then we are ready to do our plug-ins from 0 to root 2 over 2. So it's going to be 0 up to square root of 2 over 2. So this 2 we can pull out in front with the 3. So we'll have a 6 out in front. And then we just have to plug into the u to the 1/2 from 0 to root 2 over 2. So 6 is out in front. Plug in a root 2 over 2 here. So we get times the square root of 2 over 2, and that gets a 1/2 power. And then minus, plug in 0. 0 to the 1/2 is just 0. So this is just going to equal 6 times the square root of 2 over 2 to the 1/2 power. And then if you wanted, you could write this 1/2 power as a square root, so you'd actually get a square root of a square root. But again, we're not requiring simplification here. So this is good enough. Alright, one more integral here. And I look at this, and if we had one quantity underneath this cubed root on the bottom, then we could let that be our u, and we could bring it up to the top as a negative exponent again. So I look at this and I think our best bet for u is going to be equal to 5 minus x, because that simplifies the integral. And then our du is going to be equal to the derivative. Whoops, I said x and I wrote u here. It's going to be equal to the derivative of that times dx. So derivative 5 is 0, derivative negative x is negative 1 dx. So here we've got our dx. We need a negative 1, so let's multiply by negative 1 on the inside and a negative 1 on the outside. And so our dx and our negative 1 make the du. This is our u. We've still got that x that we need to rewrite in terms of u. So, well, let's see. Well, if you add x to both sides, bring this over as a positive, and subtract u on both sides, bring this over as a negative, then we get x equals 5 minus u. So I combined a couple algebra steps there. So up on the top, that x is going to be 5 minus u. So if we change this guy over, we've got that negative sign out in front, integral, the negative dx, that's our du, and our x here is 5 minus u. So on the top we've got 5 minus u. Out on the right hand side is our du from the negative dx, and then down on the bottom we've got cube root of u. So everything's changed over to u. So now change this to a fraction exponent, bring it up to the top as a negative. So you got negative integral 5 minus u. And then this will be u to the 1/3 on the bottom, du. Now bring this up to the top as a negative exponent. So this will be negative integral u to the negative 1/3 times 5 minus u du. And now multiply this guy in times each piece. So negative integral 5 times u to the negative 1/3. And then u to the negative 1/3 times negative u would be minus u. We're adding exponents here, so this is u to the 1. 1 minus 1/3 is 2/3. And that is integrating with respect to u. And now we can do power rule on each piece here. So we've got that negative out in front. Don't forget that. 5. We keep, and then add 1 to the exponent. Negative 1/3 plus 1 is 2/3. So that's going to be u to the 2/3 power. And then we divide by 2/3, which is the same as multiplying by 3/2. If you let me do that in one step. Minus, and now add 1 to the exponent here. So 2/3 plus 1, it'd be 2/3 plus 3/3, 5/3. So this is u to the 5/3. And then divide by 5/3 is the same thing as multiply by 3/5. And then plus a constant. And now all our integrating is done. So now we reverse our substitution and go back to x's, take out u and plug back in 5 minus x. And then we've got it. So this is going to be negative out in front. 5 times 3, 15 over 2. So 15 halves. And then instead of u to the 2/3, it's going to be 5 minus x to the 2/3. And then minus 3/5. And then instead of u to the 5/3, it's 5 minus x to the 5/3. Close up our parentheses, plus c. Okay, now this is a little harder substitution because we've got to rewrite this x in terms of u. So I put an easier problem on here, a partial credit problem. This one's a little bit easier to see our function and its derivative. Here I see an x squared on the outside, I see an x. So if you look at this one, you see a function u, x squared plus 3, and then its derivative is 2x. So du is 2x times dx. And here we've got the x dx. We need the 2, so multiply by 2 on the inside, compensate by multiplying by the reciprocal outside. So now 2x dx. Now we've got our du. So multiply by what you need and then compensate. So if we rewrite this guy now, we've got a 1/2 on the outside, and then integral, these two make up our du, and then this is cubed root of x squared plus 3 is our u, so cube root of u, which is just u to the 1/3. So this is just 1/2 times the integral of u to the 1/3 du. It's a little bit easier integral. And that's the idea. We want to do that substitution to change it into an easier integral. Now we're just doing power rule. Add 1 to the exponent. So 1/3 plus 3/3 would be 4/3. So we got this 1/2 out in front. U to the 4/3 power. Divide by 4/3 is the same as multiply by 3/4. And then plus your constant. And now all we have to do is plug back in our x squared plus 3. Reverse the substitution. Remember when you do a u substitution with a definite integral, you don't have to go back to x's. So notice up here, we changed our limits of integration over, wrote those in terms of u. But since you get a numerical answer on a definite integral, you don't have to change back to the x's. If you did change back to the x's and use the original 0 and pi over 4, you'd get the same answer. It'd just be more work. So here, 1 times 3 is 3 on the bottom, 2 times 4, 8, 3/8. And then instead of u to the 4/3, we're going to do x squared plus 3 to the 4/3. And then plus c on the end. And then that one's all set. All right, number 13. We want to evaluate the integral from -1 to 2 of f of x dx, where the numbers represent the enclosed area. So this is just interpreting the integral as signed area. So the integral from -1 to 2 of f of x is going to be the signed area underneath the graph of the function. So areas above the axis are counted as positive, areas below the axis are counted as negative. So the integral counts this 6 as positive, the 1.5 is negative, and the 1 is positive. So this is just going to be 6 minus 1.5 plus 1. So that's 6 and 1 is 7, minus 1.5 is going to be 5.5. And that's all there is to that. And here we're using the fact that areas are additive also. Okay, the integral from -1 to this point here, and from that point to this one, and then from here out to 2. We're adding the integral on this piece, the integral on this piece, and the integral on that piece. So we're also using that property. I just didn't state it. Here we're finding enclosed area for x cubed and 4x. So with the enclosed area, you want to count area as positive, even if it's below the axis. So let's sketch our graph here first. So get our x and y axis going. Y equals x cubed looks like this. And then y equals 4x. That's going to be a line. Use my line tool here. Look like that. So this is y equal 4x. And then we want to find the enclosed area. So we want to find that area plus that one. But notice that x cubed, odd function, because odd exponent, 4x, odd function, those have both got symmetry. So notice by symmetry that these two areas are equal to each other. So let's call this area here area 1, and we'll call this one area 2. And so the enclosed area is going to be area 1 plus area 2. but these are both the same, so by symmetry this is just going to be, let's just use the positive area, 2 times area 2. So a little different here. When we're doing enclosed area, these guys are not canceling out because we want to find the total area that's in between these two curves. So different than if you just have the single integral. So this is area enclosed. So what we're going to do is we want to find the area between these two curves. And so remember what you do is with a single curve, you're finding the area underneath the graph of the function, which is from the graph of the function down to the x-axis. So your top curve is the function, your bottom one's the x-axis. Well here, our top curve is 4x and our bottom curve is x cubed. Okay, so if you draw a vertical segment like that, you see your top part of your segment touches on 4x, your bottom on the x cubed. So area 2 is going to be the integral of the top function minus the bottom from the intersection points. So actually we've got to find those intersection points first. So that's when x cubed equals 4x. Bring this over as a negative. X cubed minus 4x is equal to 0. Factor out a common x. X times x squared minus 4 equals 0. So either x equals 0 or x squared minus 4 equals 0. Bring the 4 over as a positive. X squared equals 4. Take square roots on both sides. And x equals plus or minus 2. So at negative 2, that's going to be this intersection point. At x equals 0 is going to be that one. And then this intersection point is going to be at positive 2. So our integral is going to be from 0 to 2. And then we are going to be adding up the area between those. So it's going to be top function minus bottom function. So let's see, this top function is 4x minus the bottom function is x cubed. Okay, so this is top minus bottom. And then it's with respect to x. So you're adding up the area underneath 4x and you're subtracting the area underneath x cubed, which would be this white area, and that leaves you the area in between. So, well, once we got this set up, it's not a hard integral to do. So this is just power rule for each one of these. So 4 times the antiderivative of x is x squared over 2. And minus antiderivative of x cubed is x to the 4th over 4. And we're going from 0 to 2. This 2 cancels in here, just leaves us a 2x squared. So this is going to be 2x squared minus x to the 4th over 4 from 0 to 2. And so plug a 2 in both places, plug a 0 in and subtract. So if we plug the 2 in, we get 2 times 2 squared minus 2 to the 4th over 4 minus, if we plug the 0 in, we just get 0 and 0. So 2 times 4, that's going to be 8, minus 2 to the 4th is 16, divided by 4 is 4. So that's 4. So area 2 is 4. Our total enclosed area is twice that. So this is going to be 2 times 4, which is 8. So try to use symmetry if possible, and if you do use symmetry, don't forget to multiply by 2 when you get done. Now, to end things up here, we're doing a definite integral from the definition. So that's the 5-part definition, and we're using our right endpoint for our sums of areas of rectangles. So this is saying that, okay, the area underneath this thing is going to be a limit as n goes to infinity of Riemann sum of areas of rectangles, I equals 1 up to n, of your function, plug in the right endpoint, x of I, times delta x. So that's what we're trying to do. And our function here is x plus 3. So f of x is x plus 3. So 5 steps. Number 1, delta x is equal to b minus a over n. So that's our base. Our b is 3 and our a is 1. So this is 3 minus 1 over n, which is 2 over n. So there's our delta x. Okay, step 2, we got to find our right endpoint, xi. And remember, in general, that's a plus I times your delta x. So our a is 1 plus I times our delta x is 2 over n. So that's 1 plus, multiplying straight across, 2i over n. Step 3, find your height. So the height of the I rectangle is, take your function and you plug in your xi. So we're going to take that function and we're going to plug in this 1 plus 2i over n. Well, our function is just x plus 3, so this is just going to be 1 plus 2i over n in here for x, and then add 3 on, plus 3. And we can simplify this a little bit. 3 and 1 is 4, so this is 4 plus 2i over n. Step 4, set up your sum. So sum from I equals 1 to n of f of xi delta x is going to be the sum from I equal 1 to n, and our f of xi, our height, right here, 4 plus 2i over n. And then our base, delta x, is 2 over n here. And now simplify that as much as possible. So let's multiply this in times each piece. So 2 over n times 4 is going to be, this will be sum I equal 1 to n. 2 over n times 4, that'll be 8 over n. Plus 2 times 2i is going to be 4i over n times n squared. And now break the sum apart, so take the sum of each piece. So this will be sum I equals 1 to n of 8 over n. And then plus the sum I equals 1 to n of 4i over n squared. And then we want to factor this n out. So the thing that's varying, the variable is I, so n is a constant, so we can factor that n out on the bottom. So this n will come out on the bottom, which is a 1 over n out in front. And we'll have left the sum from I equals 1 to n of 8. Plus, and then here we want to bring the 4 over n squared out. So we just got the I left, so that's going to come out in front. So 4 over n squared, and then we've got left sum I equals 1 to n, and just I is left. And now we use the given formula. So we know that the sum of a constant from I equal 1 to n is just that constant times n. And we also know the sum from I equal 1 to n of I is n plus 1 over 2. And these I'll give you. So here the sum of 8 is just going to be 8 times n, so we've got 1 over n, and then this is just 8n. Okay, that's with c equals 8 here, so this is 8n, plus 4 over n squared out in front, and then this sum is the nn plus 1 over 2. And then simplify as much as you can. N cancels one of those guys here. 2 goes into 4 2 times. And then n and n cancel there. So we just got an 8. And then 2 times n plus 1 over n. So plus 2 times n plus 1 over n. And now multiply this guy in. So we've got an 8 plus 2n plus 2 is going to be up on top over n. And so this is simplified as far as you can, and now step 5 is to take a limit. So then your area is going to be the limit as n goes to infinity of this Riemann sum, which we worked that out and simplified it down right here. So we're taking the limit of 8 plus 2n plus 2 over n. Well, the limit of 8 is just 8. And then by dominant terms here, in this piece, the dominant terms are 2n and n. And a limit of 2n over n, the n's will cancel, and that'll just be 2. So 8 plus 2, 10. So there's our area. And then we should be able to double check here using the fundamental theorem. So here's our check. So you can always check your answer. Integral from 1 to 3 of x plus 3 dx. Do an antiderivative here. So antiderivative of x is x squared over 2. Antiderivative of 3 is 3x. And we are going to plug in 3, plug in 1, and subtract. So if we plug the 3 in here, we get 3 squared over 2 plus 3 times 3 minus, plug in the 1, we're going to get 1 squared, which is 1 over 2 plus 3 times 1, 3. So this is 9 halves plus 9, and then minus 1 half minus 3, if we distribute that minus sign, minus 1 half minus 3. So here, that's an equal sign. So, no, that's not. That's the minus sign. This is the equal sign. So 9 halves minus 1 half, these two are 8 halves, which is 4. And then 9 minus 3 is 6. So 4 plus 6, 10. And that's what we got here. So we know we did it right. So you can always use fundamental theorem to check. But this is not enough. This is not enough to get credit for this problem. I want you to go through the process and understand that a definite integral is the limit of the sums of areas of rectangles. This is base times height. Okay, sum of approximating rectangles, take a limit as n goes to infinity, error goes to 0, so this value here gets closer and closer to the actual area, which is 10.